We present AVControl, an efficient framework for training a diverse set of audiovisual controls using lightweight LoRa adapters, spanning spatially aligned guidance, video editing, camera control, and audiovisual applications. AVControl places the reference control signal on a parallel canvas, that is, as additional tokens processed alongside the generation target in the model's self-attention layers. The only trainable component is a lightweight LoRa adapter. The audiovisual backbone remains entirely frozen. The model naturally distinguishes reference from generation using the per-token time step. Reference tokens are clean, while generation tokens carry the current noise level. No new layers and no modified positional embeddings are needed. Each control modality is trained as its own independent LoRa, keeping individual runs small and focused. A video LoRa controls the visual stream while the base model freely generates synchronized audio, and vice versa for audio LoRas. Each LoRa trains in as few as 200 to at most 15,000 steps on small datasets ranging from just a few hundred to a few thousand samples. The total budget across all modalities is roughly 55,000 steps, less than 1/3 of a single VACE training run. The parallel canvas adds reference tokens to every attention layer, so more tokens mean longer runtime during inference. Our key insight is that not all control signals need the same spatial resolution. For some dense controls, each reference token maps to a specific location in the target, so we keep the full resolution canvas. But for sparser signals like camera trajectory, we downscale the reference canvas, encoding the control at a lower spatial resolution, which produces fewer tokens. The generation target stays at full resolution throughout. For camera control, a 4x reduction cuts inference by up to 50% with no loss in fidelity. We can modulate reference influence globally, locally, or temporally at inference time. Here, we sweep global strength from 0 to 1 on a depth-guided generation. At intermediate strength, the model respects coarse structure while exercising creative freedom on fine details. Note that even at 0 strength, the output resembles the scene because the text prompt itself describes the same content. We now demonstrate the breadth of modalities trained with our framework, starting with spatially aligned controls. Depth, pose, and edge maps each guide the generation through their own independently trained LoRa. The outputs faithfully follow the spatial structure while maintaining natural motion and visual quality. The framework naturally extends to video editing. Inpainting and outpainting share a single LoRa, unified by mask representation. Masked regions in the reference canvas are filled with a fixed color, and the model learns to reconstruct them. The same inpainting LoRa handles outpainting by simply masking the border regions, extending the video canvas beyond its original frame. Unlike inpainting, local edit does not require a mask. The model learns to add or remove objects from a text prompt alone, including their side effects like shadows and reflections. Video detailing enhances resolution and recovers fine textures that were lost in the low-resolution input. We support 2 camera control modes, generating diverse motions from a single image and re-rendering an existing video at a new camera trajectory. We control both camera extrinsics and intrinsics. From a single image, we generate video with a specified camera motion. The desired trajectory is encoded as a warped grid on the reference canvas, and the model animates the scene accordingly. From the same source image, different camera trajectories produce diverse outputs. The model faithfully follows each trajectory while maintaining scene consistency. Given an existing video, we estimate its full camera parameters and re-render the scene at a new trajectory while preserving the original scene dynamics. This also supports per-frame field of view changes. From the same source video, different camera trajectories re-render the scene with distinct viewpoints while preserving the original scene dynamics. In sparse track control, point tracks are rendered as colored dots on a black canvas. The LoRA generates a video that follows these trajectories, enabling fine-grained control over object motion. From the same source video, different sparse track patterns produce diverse outputs. The model faithfully follows each set of trajectories while maintaining scene consistency. Cut on action re-renders a scene from a substantially different viewpoint while preserving the action and timing. Another example, the parallel canvas handles references that are temporally aligned but very different spatially from the target, generating multiple diverse angles from the same source. We now showcase audiovisual applications. Audio intensity control generates audio whose temporal dynamics follow the visual content. The waveform below shows how the generated audio energy tracks the on-screen action. Speech-to-ambient embeds clean speech within ambient sounds, matching a described scene. First, the clean speech input.
Greg, we can spend as long as we like in the tavern and it won't.
Now, the output, the same speech embedded in an ambient environment with synchronized video.
Greg, we can spend as long as we like in the tavern and it won't.
Who is Talking generates multi-person talking video with synchronized lip motion from an abstract layout of colored bounding boxes, indicating who speaks when.
How are you doing? Did you hear about AVControl?
Oh yeah, I did. Pretty cool.
Side-by-side comparison on depth-conditioned generation from the VACE benchmark. Our method better preserves spatial structure and produces higher visual quality, as reflected in the V-bench scores. Side-by-side comparison on pose-conditioned generation from the VACE benchmark. Our method achieves more faithful pose adherence and better motion quality. We evaluate our method on 4 independent benchmarks. On the VACE benchmark, we outperform all baselines across depth, pose, inpainting, and outpainting. On the ReCamMaster camera benchmark, we achieve the highest clip F score. For audio intensity control, we achieve the highest inception score, and for Who is Talking, we achieve the best expression and visual fidelity scores. To summarize, AVControl trains lightweight LoRA adapters on a frozen audiovisual backbone to enable diverse control modalities. Over 13 modalities spanning video, camera, editing, and audio are each trained independently in minutes on a single GPU with no changes to the underlying model. Adding a new control requires only a small dataset and a short training run. Despite this simplicity, we achieve state-of-the-art results across 4 independent benchmarks. Thank you for watching. For more details, please refer to our paper.